So next I am going to discuss the term normal reaction, and I am also going to discuss some examples in bodies in contact. First, I would like to discuss the term normal reaction. So in general, when two bodies are placed in contact, if the surfaces in contact are smooth, then the force exerted by the surface of one body on the surface of other body placed in contact with it acts normal to the surfaces in contact. So in general, when two bodies with smooth surfaces are placed in contact, the contact force means the force exerted by the surface of one body on the surface of other body acts perpendicular to or normal to the surfaces in contact. So let us consider a block of mass m resting on a smooth horizontal floor. So I consider a block of mass m resting on a smooth horizontal floor. Let us consider a block of mass m resting on a smooth horizontal floor. So due to the contact, the block exerts a force on the surface. So when the block rests on the horizontal surface of the smooth floor, we can say that the block presses the surface of the floor vertically downwards. The block exerts a force on the surface of the floor vertically downwards. The block rests on the horizontal surface. The block presses the surface of the floor vertically downwards. So the block exerts a force on the surface of the floor in the vertically downward direction. According to Newton's third law, to every reaction, there will be an equal and opposite reaction. Here action is the force exerted on the surface of the floor by the block, which acts vertically downwards. So direction of the reaction will be opposite to the action. If action is vertically downwards, reaction will be directed vertically upwards. Action is the force exerted on surface of floor by the block, which acts vertically downwards. This reaction will be the force exerted on block by the surface of the floor. Which acts vertically upwards. So this reaction force exerted on block by the surface of floor acts normal to the surface of the floor, means perpendicular to surface of floor. This reaction force, we call it as normal reaction. The modulus or magnitude of this normal reaction force is denoted by N. Of course, at present I am not discussing a problem. I am just discussing the term normal reaction and how normal reaction force acts on a body in different situations. So when a block is resting on the horizontal floor, the block presses the surface of floor vertically downwards. So the block exerts a force on the surface of floor in the vertically downward direction. So the force exerted on the surface of floor by the block acts vertically downwards. So according to Newton's law, to every reaction there is always an equal and opposite reaction. Here action is the force on floor by block. So reaction will be the force on block by the floor. This reaction force on block by the floor we call normal reaction because it acts normal to surface in contact. In some of the numerical examples, you may be asked to find the magnitude of the force on floor by block. When I asked some students in 11th class, I used to observe that when I asked them what is the force on floor by block, they simply used to say mg. That's why I have specifically discussed the term weight of the body in my previous class. Weight of the block is not the force by the block on floor. Weight of the block is the gravitational force on block by the earth. Weight of the block is the gravitational force on the block by the earth. The weight mg acts on the block even if the block is not placed in contact with the floor. This action-reaction pair which I have shown in the figure, they can be called as contact forces between the block and the floor. These forces come into action. These forces arise due to the contact between the block and the floor. So when you are asked to find magnitude of the force on floor by block in any numerical problem, you have to find the magnitude of this N, that is normal reaction force on block by floor. Because from Newton's law, action and reaction forces always have same magnitude. So if N represents modulus or magnitude of the normal reaction force on block by floor, then the magnitude or modulus of the force on floor by block will also be equal to N. Of course, N may be equal to mg in magnitude in some of the problems, but you cannot make a generalization that N equal to mg in every example. The magnitude of this normal reaction force depends on situation or the forces acting on the body, other forces which act on the body. But suppose when you draw a free body diagram for the block while solving numerical problems, when you are drawing a free body diagram for a block resting on the floor, in the free body diagram for the block, we must show only the forces which are acting on the block. But we should not show the force by block in the free body diagram of the block. So this force on floor by the block should not be shown in the free body diagram for the block. Only the reaction force, I mean normal reaction force on block by the floor is shown in the free body diagram for the block. And observed with some students that they mistake that normal reaction force always acts vertically upwards in every example. Normal reaction force may not act vertically upwards in every example. Of course, in the example I have shown here it may be directed vertically upwards, but not in every case. So let us consider a block resting on the inclined surface of a fixed inclined plane which makes an angle theta to the horizontal. Let us consider a block of mass m resting on the inclined surface of a smooth inclined plane which makes an angle theta to the horizontal. Let us suppose the block sometimes, some cases may be held at rest with the help of some light rod or string connected to a rigid wall or rigid support. Now in this case, of course, at present I am not discussing any problem. We will discuss the problems later. At present I am just discussing the term normal reaction. So here the block is resting on the inclined surface of a smooth and fixed inclined plane where the inclined plane makes an angle theta to the horizontal. So due to the contact, the block presses the surface of the inclined plane with some force. So the block exerts a force on the surface of the inclined plane. So when surfaces in contact are smooth, then this force exerted on surface of the inclined plane by block acts perpendicular to surface in contact and directed towards the surface in contact. According to Newton's third law, to every action there will be always an equal and opposite reaction. Here action is the force exerted on the surface of the inclined plane by the block, which acts perpendicular to the surface of the inclined plane and directed towards the surface of the inclined plane. So the direction of the reaction will be opposite to the action. Here action is the force exerted on surface of the inclined plane by the block. So reaction will be the force exerted on block by the inclined surface. This reaction force exerted on block by the inclined surface, we call it as a normal reaction. It is called a normal reaction because it acts normal to the surfaces in contact, means perpendicular to surfaces in contact. You can observe that in this case, the normal reaction force on the block is not directed vertically upwards. From the situation, you can observe that in this case, normal reaction force on block by the inclined surface makes an angle theta with the vertical direction. This theta is same as the angle of inclination of the inclined plane to the horizontal. But of course, here also you can say the action reaction force are same in magnitude. So if N is the magnitude of normal reaction force on the block by the inclined surface, then the modulus or magnitude of this force exerted on surface of the inclined plane by the block will also be equal to M. Now let us consider another case where block is pressed against a vertical wall by applying a horizontal force. Again, here we are not solving a problem at present. We are only just discussing how normal reaction force acts on the block in different situations. Let us consider a block of mass m, which is pressed against a vertical wall by applying a horizontal force. Let us consider a block of mass m pressed against a vertical wall by applying a horizontal force. So the horizontal force exerted on the wall by the block acts perpendicular to the surface of the wall and directed toward the wall. So the block presses the surface of the wall towards left. So we can say that block exerts a force on surface of the wall towards left. So the force exerted, the horizontal force exerted on surface of the wall by the block, the horizontal force exerted on the surface of the wall by block acts towards left side. According to Newton's third law, to every reaction there is always an equal and opposite reaction. Here action is the force exerted on surface of the wall by the block which acts towards left side. So directly the reaction will be opposite to the action. So reaction will be directed towards right. This reaction will be the force exerted on block by the surface of the wall. So this reaction force exerted on block by surface of the wall we call normal reaction. Because it acts normal to surface in contact. The magnitude of this normal reaction is usually denoted by N. So here action is a force, horizontal force on surface of wall by the block which is directed towards left side. Reaction will be the horizontal force exerted on block by the wall which acts towards right side. Again action and reaction will be same in magnitude. If N is the magnitude of normal reaction force on block by wall, then modulus of force on wall by the block can also be written as equal to N. You can observe that in this example, normal reaction force is directed horizontally. The first example, that is when the block rests on the horizontal floor, normal reaction force on the block by floor is directed vertically upwards. The second example, that is for the block resting on the inclined surface of a fixed inclined plane. The normal reaction force on the block by the inclined surface acts perpendicular to the inclined surface and directed away from the inclined surface. That means here normal reaction force acts at an angle theta with a vertical. But in each case you can observe that the normal reaction force on the block by the surface in contact acts perpendicular to the surface in contact and it is directed away from the surface in contact. So in general, when a block is placed in contact with a surface, the normal reaction force exerted on the block by the surface in contact acts perpendicular to surface in contact and will be directed away from the surface in contact. So I would like to show this conclusion on the screen so that those who are writing the notes, they can write this point also, which I am going to show on the screen. So earlier I have discussed the term weight here. So here I have given the definition of the term weight here. I mean, it is the meaning of the term weight of a body. So those who are copying the notes, they can copy these 2 points which are shown on the screen now. Weight of a body present near the Earth's surface is the gravitational force exerted on the body by the Earth. So in vector form, we write W bar equal to mg bar. Here m small m is the mass of the body, and g bar is the acceleration due to gravity. From magnitude of the weight of the body can be written as W equal to mg. Next, look at the term normal reaction. When a block is placed in contact with a surface, the normal reaction force on the block by surface in contact acts perpendicular to surface in contact, directed away from the surface in contact. So those who want to copy these 2 points can take a pause and copy down these 2 points. These conclusions, these definitions you must, these 2 points you have to remember. So while solving problems in Newton's laws and friction and other topics in mechanics, remember that when a block is placed in contact with a surface, the normal reaction for the block by surface in contact always acts perpendicular to surface in contact and directed away from surface in contact. So we are going to draw the free body diagram for the block. In the free body diagram for the block, we must show only the forces which are acting on the block. So the first force which acts on the block is its weight mg, which acts vertically downwards. The weight of the block is the gravitational force on the block by the Earth. Then secondly, the normal reaction force on block by the floor acts vertically upwards. The pulling force applied on the block acts at an angle of 53 degrees above the horizontal. All the 3 forces act in the vertical plane. So the diagram shown in the figure is in the vertical plane. So in the free body diagram for the block, we must show only the forces which are acting on the block, but not the forces exerted by the block. So the force by the block on the floor should not be shown in the free body diagram of the block. Only the reaction force on block by the floor should be shown. Here N represents the magnitude of the normal reaction force on block by the floor, which acts vertically upwards. So this is a free body diagram for the block. Next we choose X and Y axis. In this case, the block moves along the horizontal floor. Therefore, the horizontal direction, which is coincides the direction of the motion of the body, we can choose it as x-axis. In vertically upward direction, we can take it as positive direction of y-axis. The pulling force is inclined to both x and y-axis. Therefore, you can resolve the pulling force into rectangular components. parallel to x and y axis. For that, you can construct a rectangle with adjacent sides along x and y axis such that the pulling force acts along the diagonal of the rectangle. The x component of pulling force will have magnitude f cos 53 degrees. The vertical component of pulling force will have magnitude f sin 53 degrees. So in this case, the block moves along x-axis. The acceleration of the block is directed along x-axis. So resultant force is directed along x-axis. The block has no motion parallel to the y-axis. So y component of resultant force of the block is 0. If the y component of the resultant force of the block is 0, the resultant of all the external forces acting on the block will be equal to the x component of the resultant force. The only force which acts along x direction is the component of pulling force, which has magnitude f cos 53 degrees. From Newton's second law, the resultant of all the forces acting on the block is equal to product of the mass of block and its acceleration. You are given the weight mg of the block equal to 100 Newton. The acceleration due to gravity is given as 10 meter per second square. So you can substitute g equal to 10 meter per second square on the left hand side. You get the mass of the block as 10 kg. So you are given the acceleration of the block in the problem as 3 meter per second square. So you can substitute here cos 53 degrees equal to 3 by 5. The mass of block is 10 kg. The acceleration equal to 3 meter per second square. So from this you get magnitude of the pulling force on the block equal to 50 Newton. So that is one of the answers to the problem. To find the magnitude of the force on floor by the block, to find the magnitude of the force on the floor by the block, you have to find the magnitude of the normal reaction force on block by floor. So along y-axis, the vertical component of the pulling force with magnitude f sin 53 degrees acts along positive axis. Let n represent magnitude of normal reaction on block by the floor, which is also direct along positive axis. The weight mg of the block is directed vertically downwards in the negative direction of y-axis. Therefore, y component of resultant force of the block is equal to n plus f sin 53 degrees minus mg. But in this case, the block moves along x-axis in the horizontal direction. The block has no motion in the vertical direction. The block has no acceleration in the vertical direction. So y component of acceleration is 0, y component resultant force must also be 0. Therefore, the magnitude of the normal reaction force on block by the floor will be equal to mg minus f sin 53 degrees. The weight mg of the block is given to 100 newtons. We got f equal to 50 newtons. Sin 53 degrees equal to 4 by 5. So magnitude, if you simplify this, you get magnitude of the normal reaction force on block by the floor, 60 Newton. Answer is 60 newtons. You are asked to find magnitude of the force on floor by the block. From Newton's third law, magnitude of the force on floor by the block is same as the magnitude of the normal reaction force on block by the floor, which is equal to 60 Newton. So for second part of the question, answer is 60 Newton. So with this we have finished the problem. So if you want to copy down the solution of the problem, you can copy down the solution of the problem. In case you need more time to copy the solution of the problem, you can take a pause and take your time to copy the solution of the problem. Look at the next problem, problem number 3. I will read out the problem. Two blocks of masses M1 and M2 are placed in contact on a smooth floor, horizontal floor, and a pushing force of magnitude F is applied on M1 at an angle theta with the vertical as shown in the figure. Find the magnitude of contact force between, first part question M1 and M2, second part of the question M1 and the floor. Let's see the diagram then. Third part of the question. In the third part of the question, you have to find magnitude of the contact force between M2 and floor. Look at the diagram. So look at the information diagram. M1 is given to be, take M1 equal to 3 kg, M2 equal to 2 kg, F equal to 15 Newton, theta equal to 53 degrees, G equal to 10 meter per second square. So that's the diagram shown in the figure. The angle shown in the figure is theta. The angle with the vertical, with the pushing force makes, that is theta. So, if you want, you can copy the diagram. I am going to discuss the solution of this problem. So, it is given that the two blocks M1 and M2, it is given that the two blocks M1 and M2 are placed in contact with each other and also placed on a smooth horizontal floor. And the pushing force is applied on M1 at an angle theta with the vertical. The magnitude of the pushing force denoted by F. So during the motion, M1 pushes M2 towards right. So during the motion, the mass M1 pushes the mass M2 towards right. Here both the blocks move towards right with the same acceleration. So during the motion, the mass M1 pushes the mass M2 towards right. So during the motion, the mass M1 exerts a force on M2 towards right. When two bodies with smooth surfaces are placed in contact, the contact force between the two surfaces, the contact forces between the surface of two bodies act normal to surface in contact. Let F dash denote the magnitude of the force on M2 by M1, which acts towards right. According to Newton's third law, To every action, there will be always an equal and opposite reaction. Here action is the force on M2 by M1, which acts towards right. Again listen, during the motion, the mass M1 pushes the mass M2 towards right. So we can say that the mass M1 exerts a force on M2 towards right. According to Newton's third law, to every action, there is always an equal and opposite reaction. Here action is the force on M2 by M1, which acts towards right. The magnitude or modulus of this force is denoted by F dash. So direct of the reaction will be opposite to action. So reaction will be to the left side. If action is the force on M2 by M1, the reaction will be the force on M1 by M2. If action is the pushing force on M2 by M1, the reaction will be the force on M1 by M2. According to Newton's law, action and reaction forces always have same magnitude. So if F dash represents the magnitude or modulus of the force on M2 by M1, then the modulus or magnitude of the reaction force on M1 by M2 is also equal to F dash. So we can say that F dash is the magnitude of the contact force between the two blocks. So here now I am going to draw a separate free body diagram for each block. The forces which act on M1 must be indicated in the free body diagram for M1. The forces which act on M2 must be indicated in the free body diagram for M2. FBD is the short form for free body diagram. The forces which act on M1 must be indicated in the free body diagram for M1. The forces which act on M2 must be shown in the free body diagram for M2. So here action is, when you consider the contact force between the two blocks, action is the force on M2 by M1. So it should be indicated in the free body diagram for M2. The reaction is the force on M1. The forces which act on M1 should be shown in the free body diagram for M1. So reaction force should be shown in the free body diagram for M1. Action and reaction forces act on different bodies. That's why they don't cancel. Now the pushing force has a magnitude F, denoted by F, acts at an angle theta with a vertical direction. Graphically, a given vector can be drawn at different places in the diagram without changing its magnitude and direction. So you can represent the pushing force in this manner. Like this. This angle is also zero. Graphically, you can draw a given vector different place in the diagram without changing its magnitude. And this is a force F bar. The same force F bar can be represented like this. So in the free body diagram, usually we try to represent all the forces drawn from same point such that tails of all the vectors coincide. Then next, the weight of the block acts vertically downwards. M1G is a gravitational force on M1 by the earth. The normal reaction force on M1 by the floor acts perpendicular to surface of the floor in contact and directed away from surface of the floor in contact. As I discussed earlier, In general, when the block is placed in contact with a surface, the normal reaction force on the block with the surface in contact always acts perpendicular to surface in contact and directed away from surface in contact. Here N1 is the magnitude of normal reaction force on the mass M1 by the floor, which acts perpendicular to the surface of the floor in contact with M1 and directed away from surface of the floor. You can say N1 is the magnitude of the contact force between the mass M1 and the floor. So we completed the free body diagram for M1. Now coming to the mass M2, the weight M2G is the gravitational force on M2 by the earth which acts vertically downwards. Let N2 denote the magnitude of the normal reaction force on M2. Let N2 denote the magnitude of the normal reaction force on M2 by the floor, which acts perpendicular to surface of floor and directed away from surface of floor in contact, acts vertically upwards. So in this case, both the blocks move towards right with the same acceleration. So I choose the horizontal direction, which is the direction of the motion of each block as positive direction of x-axis, in vertically upward direction as the positive direction of y-axis. As explained in the free body diagram technique, if one of the forces acting on the body is inclined to both x and y axis, then it should be resolved into rectangular components parallel to x and y axis. So the pushing force inclined to both x and y axis will resolve the pushing force into rectangular components parallel to x and y axis. For that, you have to construct a rectangle with adjacent sides parallel to x and y axis, such that the pushing force acts along the diagonal of the rectangle. So this component of the pushing force, which makes angle theta with the direction of the pushing force, will have magnitude f cos theta. The horizontal component of pushing force will have magnitude of sin theta. The vertical component of pushing force applied on M1 will have magnitude f cos theta, which acts vertically downwards. The pushing force applied on M1 should be shown in the free body diagram for M1. The horizontal component of pushing force will have magnitude of sin theta. Here none of the two blocks have motion in the vertical direction. So y component of the resultant force on each block is 0. So resultant force on M1 can be written as equal to the x component of the resultant force, because the mass M1 has no acceleration parallel to y-axis. Fy is 0. If Fy is 0, the resultant force on the body equal Fx. The horizontal component of pushing force, which has magnitude f sin theta, acts along positive direction of x-axis. The reaction force on M1 by M2 with magnitude f dash acts toward left side, the negative direction of x-axis. So magnitude of the x component of the resultant force on M1 can be written as f sin theta minus f dash. From Newton's second law, the resultant of all the forces acting on M1 will be product of its mass and acceleration. Let A be the common acceleration of the blocks. Next, similarly, the second mass M2 also has no motion in the vertical direction. So the y component resultant force on M2 is 0. So resultant force on M2 is equal to resultant of forces acting in the x direction The only force which acts on M2 in the horizontal direction of X direction is F dash. From Newton's second law, resultant force on M2 can be written as product of its mass and acceleration. Here acceleration is same for both the blocks. So you can add the equations 1 and 2. So F sine theta minus F dash plus F dash equal to M1A plus M2A. So you can write F sine theta equal to M1 plus M2 into A. So the magnitude of the acceleration of the blocks is equal to F sine theta by M1 plus M2. So you are asked to find magnitude of the contact force between the two blocks. So magnitude of the contact force between the two blocks M1 and M2 denoted by F dash. From second equation, which is equal to M2A. Now we can substitute A equal to F sine theta by M1 plus M2. Now we can substitute all the given values and simplify it. F is given to 15 newtons, M2 equal to 2 kg, F is given to 15 newtons, theta is 53 degrees, M1 equal to 3 kg. So this you can simplify it yourself. So you can simplify that yourself. You get the answer. So 2 into 10 into 4 by 5 Newton. That comes out to be 16 Newton. So answer for the first part of the question is 16 newtons. To find the magnitude of the contact force between M1 and the floor, you have to find normal reaction N1. So for the mass M1, the bicomponent resultant force, which we denote by Phi, equal to N1 minus mg minus F cos theta. But the mass M1 has no motion in the vertical direction. So y-component of the resultant force on M1 must be 0. So magnitude of the normal reaction force on M1 by the floor is equal to mg plus F cos theta. Here mass, M1g, it should be. So M1 is given to be 2 kg. M1 is given to be 3 kg. G is 10 meter per second square. F is given to be 50 newtons. Theta is 53 degrees. Cos 53 degrees is 3 by 5. We can simplify this. So magnitude of the normal reaction force on M1 by the floor. Here you take N1 as 3 kg. So 30 plus 30, 60 Newton. So this is the answer for second part question, whereas this is the answer for the first part question. So N1 is the normal reaction force on M1 by the floor. That means N1 can be taken as the magnitude of the contact force between M1 and the floor. Similarly, you can find magnitude of the contact force between M2 and floor. That means you have to find N2. Can equate the y component of the resultant force on M2 0. You can look at the free body diagram for M2. So of course I have finished first two parts of the question. In case you want to copy the solution of the problem, you can copy down the solution of the problem. In case you need more time to copy the solution of the problem, you can take a pause and copy the solution of the problem. So for first part of the question, you get 16 Newton is the answer. That is magnitude of the contact force between M1 and M2. For second part of the question, you get 16 Newton as the answer. That means magnitude of the contact force between M1 and the floor is 16 Newton. Coming to third part of the question then, look at the free body diagram for the mass M2. The y component of the resultant force on M2 is equal to N2 minus M2G. But the mass M2 has no motion in the vertical direction. There is no acceleration in the y direction. So y component resultant force on M2 is 0. So N2 is equal to M2G. M2 is given to be 2 kg and G is given to be 10 meter per second square. So magnitude of the normal reaction force on M2 by the floor, 20 Newton. Or you can say magnitude of the contact force between the second mass M2 and the floor is 20 Newton. So for third part of the question, answer is 20 Newtons. Okay, I will continue my class in the next class. I will continue the discussions. Of course, this problem is completed. In my next class, I will be discussing about motion down a smooth and fixed inclined plane.